So the thermal management by using heat pipe technology involves conventional heat pipe, closed loop pulsating heat pipe. So these devices are actually used for transferring heat within short distance. So we'll see in detail how these devices are used for thermal management of uh, electronics as well as some other methods for cooling. Now these are the learning objective: to know various cooling techniques for thermal management, to study various heat pipe working principle and parameters affecting the performance, to study the various applications of heat pipe in electronic cooling. So this is the thing which we will discuss in detail in this particular session. Now electronic cooling methods, in earlier days this electronic cooling methods was done by natural convection or by a forced convection. As we are aware of the natural convection, in which the cooling of the electronics devices takes place because of natural flow of fluid. Second, it is a forced convection. In forced convection, the external fans can be used, just like in case of laptops. You might observe the fans which are installed for the cooling purpose. So first one, it is a natural convection. Second one, it is a forced convection. So that was a single phase technology that was used in some earlier days. Then a two-phase technology can involve spool boiling, falling film, liquid jetting pigment, spray, mist cooling, flow boiling. So this was comes under two-phase technologies where the two phases was present. Now next thing, a latest one, it is a special technology which uses thermoelectric devices, heat pipes, various designs and pulsating heat pipes. The drinking bird is a popular toy which has amused generations of children. Now this is the basic behind the pulsating heat pipe. Now this toy, actually the reason for the development in the pulsating heat pipe. Now how we'll see this toy first. Now with this toy you can observe there are two things. First one, it is a head, and second one is a tail. And this head and tail is actually connected with the help of one tube. So this is joining this head and tail. Now second thing, other thing you can observe is you will observe a red fluid inside. So that is a methylene chloride which is having a quite less boiling point than water. So the methylene chloride has boiling point nearly around 40 degrees Celsius. So that's quite less value, whereas the water has a boiling point 100. So what happens? There are sustained oscillations. We can say upright, up and down movement of this particular duct. We are not having any external power. Still, we say the duck starts drinking water. Again, it comes upright, and again it is started drinking water. So how this is actually happening? So we'll see in this detail. Now, first thing has to be understood is the head of the duck is actually covered with a fuzzy cloth. Then inside of that we can observe a red fluid is already there, and we have a tube which is connecting that head as well as a tail. Now first thing is, whenever the duck is drinking water, or it seems like a drinking water, so in such case what happens, the water, it is in contact with the methylene chloride over the glass tube. So what happens, the methylene chloride, it expands, and because of this expansion, so the more amount of fluid will be available in the tail, that pushes the bird upright. So we see the bird seems to goes upright because of this. In second case, what happens, when the bird goes upright, the fuzzy cloth which is attached over there, so whatever the water absorbed by this fuzzy cloth, now it evaporates. And once this is evaporates, the head of the duck subjected to low pressure inside, and because of this low pressure, what will happen, the high pressure which is available at the other end, that is in the tail, pushes the liquid which is available, that is a red liquid, methylene chloride, forward. And in that case what happens, again the fluid is coming towards the head, and that result in a downward motion of the duck. So this is, in this way we look like the duck is drinking the water, but one thing has to be remember, there is no such direct contact of that red fluid and the water. The duck is not at all drinking the water, it is just coming in contact through the glass tube. So there is no such direct contact, and this evaporation is actually responsible for creating low pressure inside, and this low pressure, uh, whatever is taking place at the head, and the high pressure at the tail, so that pushes the red liquid, that is a methylene chloride, towards the head, and that results in a sustained oscillation, and that's why we used to observe the the bird, or we can say the drinking bird, starts drinking water. So this is how we say the basic thing which is behind the pulsating heat pipe. So the phenomena of pulsating heat pipe is comes from this drinking bird. Now this is a conventional heat pipe. In a conventional heat pipe, you can observe there is evaporator section, there is a condenser section, and this evaporator and condenser section are separated by adiabatic section. So in evaporator section, heat is absorbed. In the condenser section, heat is rejected. So no heat is absorbed or rejected in between the adiabatic section. And because of the gravity, the whatever the liquid which is formed after condensing, that is again coming back to the evaporator section, and this process continues. So this is the example of a conventional heat pipe. So you can observe with the help of the image which is at the bottom. You can say 1 2 3 process. So the process is continuous. Then this is an example of a conventional heat pipe. So again, this is an example of conventional heat pipe. If you run this animation, what will observe? The fluid, the vapors are formed, this vapor going towards the condenser section, and it is coming back towards the evaporator section. Then again it is a loop heat pipe. So loop heat pipe, if you observe again, so loop heat pipe is generally considered for the heat pipe which is whose ends are closed. So in that cases it will be called as a loop heat pipe. So this is an example where the heat is absorbed, heat is rejected. So we say two working fluids which are coming in contact. So heat exchange process is actually taking place. So this is the example of one of the loop heat. Now next one is a case of open and closed loop pulsating heat pipe. So there are two cases. One is open loop heat pipe. Second one is a closed loop pulsating heat pipe. So the closed loop pulsating heat pipe, both the ends are closed. In case of open loop pulsating heat pipe, both the ends are actually not closed. So you can see n number of turns in between. So there can be n number of turns for a closed loop pulsating heat pipe as well as a open loop pulsating heat pipe, provided that both the ends are actually joined together with respect to each other. In case of a closed loop pulsating heat pipe, so the complete fluid flow visualization can be observed in case of a closed loop pulsating heat pipe. Again, some filling wall is always provided, but using a filling wall sometimes create kind of drawbacks, maybe because the leakage of fluid to the surrounding. So over the period of time, the leakage of fluid will always takes place toward the surrounding. So having a filling wall, it's one of the good option for having a multiple fluids in a same heat pipe, but that also creates some kind of disadvantages in terms of leakage of fluid that can take place over the period of time. Next thing, this is the animation again. So this is one of the simulation which shows how the fluid flow is actually developed once the heating is started in the evaporator section, and how the fluid is rejecting heat into the condenser section. So this is the animation which is prepared with the help of ANSYS 2019 release 2 version. The working of pulsating heat pipe depends on the three principles. You can observe there are three principles. First one is thermodynamic principle, second one fluid dynamics, and last one is the heat transfer principle. Now first thing has to be understood is we have a heat pipe which is heated in the evaporator section, then heat is rejected in the condenser section. In between that we have a adiabatic section. So what happens once heat is given into the evaporator section, the water starts converted into steam. So during this process, as we have some 30 to 70% of the filling ratio, so with this what alternate liquid and vapor slug starts formation. This formation will goes towards this alternate liquid and vapor slug move towards the capillary tube, or diameter is comparatively less, and that results in the alternate liquid and vapor slug which are moving. So what happens? The alternate liquid and vapor slug means we have sensible heat also, we have latent heat also. Sensible heat, it associates with the liquid. We have latent heat which is associated with vapor slug. So we can say the fluid flow is actually developed, and that results in the fluid which is moving from evaporator section to the condenser section. So this happens against gravity. So we say sensibility is also involved, latency is also involved. Then you can see the flow against the gravity is taking place because of difference of temperature, difference of pressure, that results in the flow of fluid from evaporator section to the condenser section. So the fluid dynamic principle is involved. We have we can say next thing is the heat transfer principle. What we have, the fluid which is available in the evaporator section, it is there is a copper tube, and copper tube, inside the copper tube we have a working fluid. So we have to take a water bath or any other, you can say, fluid which is transferring heat to the copper tube, and copper tube is transferring heat to the inside fluid which is available. Now this inside fluid, that is alternate liquid and vapor slugs are formed once heat is given. Then this alternate liquid and vapor slug move towards the condenser section. There again it rejects the heat to the the fluid which is available in the condenser section. So we have a heat transfer principle, means heat is absorbed at one place, heat is rejected at the other place. So heat is absorbed in the evaporator section, heat is rejected in the condenser section. The fluid dynamic principle, it is basically the flow of fluid which is taking place against the gravity. So that is because of difference of pressure which is created in the evaporator section and the condenser section. Now the parameters which are affecting the performance of closed loop pulsating heat pipe. First one is tube diameter. The diameter of tube is selected approximately as 2 to 3 mm because the capillary action should take place in the closed loop pulsating heat pipe. So diameter is one of the important parameter because the liquid and vapor slug will flow through it. So the tube diameter is one of the critical. Diameter of 2 mm is already selected for pulsating heat pipe. Working fluid also is one of the important parameter. If the boiling point of working fluid is quite less, if the boiling point of working fluid is quite high, so that also affects the performance of a closed loop pulsating heat pipe. Next thing is the filling ratio. The filling ratio cannot be 0. If it is a 0, it will work like a solid. If it is a filling ratio is 100%, it will work like a thermosiphon. So we require a filling ratio which is from somewhere around 30 to 70% of the total volume of the we can say tube is filled with the fluid. So that is a filling ratio. It can be around 30 to 70%. Compatibility of heat pipe material. The compatibility of working fluid with the heat pipe material is also one of the parameters that affects the performance of a closed loop pulsating heat pipe. Next thing is the number of turns, that it also affects the performance of a closed loop pulsating heat pipe. In case of compatibility, sometimes some fluids are compatible with copper, some fluids are compatible with stainless steel, some fluids are compatible with aluminum. So these things are also taken into consideration while determining the performance. Now see the boundary conditions of closed loop pulsating heat pipe. Now first thing you can observe is the diameter. So diameter cannot be too less, diameter cannot be too large. So if the diameter is less, say it is considered to be around 2 to 3 mm. So it cannot be more than 3 mm because the capillary action will not take place. So the diameter is also one of the critical parameters. It cannot be too high. Other thing, the diameter is after the diameter we have filling ratio. So once the filling ratio is concerned, so the filling ratio cannot be 0, the filling ratio cannot be 100%. So it must be certain value which is somewhere around 20 to 80 or somewhere around 30 to 70 depending on the, we can say, your experimental setup. So if it is 0, it means that it is completely a solid which is transferring heat. If the filling ratio is taken as 100%, if it is 100%, it means that it will work as a thermosiphon. So this is how the filling ratio is. So 0%, it cannot be there, it should not be there. It will work like a solid. If it is 100%, so it will work like a thermosiphon. Now next thing is the filling ratio whenever we are considering. So some range is always selected around 30 to 70%. Now what is filling ratio? Filling ratio is the total volume of the fluid, total volume of the pipe which is filled with the fluid, that is called as the filling ratio. Next thing, heat input. Heat input cannot be too low or heat input cannot be too high. So heat input is too low, it means in such cases you don't have the, we can say, the vapor formation that is taking place. If the heat input is too high, in such cases what will happen, the dry out of the working fluid will take place. So that is also, we can say, not good. So we must have certain we can say heat input. It cannot be too high or as well as it cannot be too low. So diameter, then the filling ratio, and last one heat input. Next thing, that is our temperature ranges of working fluid. So these are some temperature ranges of working fluid. Say we have helium, nitrogen, ammonia, acetone, methanol, ethanol, heptane, water. So these are operating ranges. So quite low operating ranges also there. So we can say low operating ranges, some medium operating ranges, and then we can have a high operating ranges also. Like say water, if we consider 330 to 200. The next thing is the compatibility of working fluid. So here the copper, aluminum, stainless steel, nickel are mentioned. So there are different working fluid: water, acetone, ammonia, and methanol. So based upon the usage, based upon the literatures, and we say based upon some assumptions, these are the things which are mentioned. So copper recommended by usage, acetone is also recommended by usage, ammonia it is also recommended by usage. So based upon the literatures which other researchers have done, methanol also it is recommended by usage. Next one, aluminum, it may generate gases. Acetone recommended by literatures, ammonia is recommended by usage, methanol is recommended by literature. Stainless steel again may be compatible with water and acetone, recommended by usage for ammonia, then may be compatible with methanol. So next thing is nickel. So these are some of the things which is we can say compatibility of the tube material with respect to the working fluid. So that is also one of the parameters that has to be taken into consideration while selecting a working fluid for a given experimental setup. The applications. So thermal management of laptop using pulsating heat pipe, thermal management of seal LED lamp using pulsating heat pipe, waste heat from electronic equipment can be utilized for drying, satellite thermal control by using pulsating heat pipe. So these are some of the applications. This is one of the example of laptop cooling. So here the CPU generates heat. That CPU, whatever the heat from the CPU is taken out with the help of this particular heat pipe arrangement. And at other place, what we have a fan which is rejecting, which is responsible for rejecting heat from the fluid. So this is how the continuous cycle is maintained. So whatever the vapor form is there, vapors are formed. They are going towards the other section. So heat is rejected from there, and again the liquid is coming back to the evaporator section. So this is how the heat you can say taken from the CPU. So heat is rejected, heat is absorbed. So this is how the process is taking place in case of a heat pipe which is used in laptops. Then LED lamps. In LED lamps also generate too much of heat. So this heat can be taken out with the help of a pulsating heat pipe technology. So you can provide the heat pipe at the back side of LED lamps, so that will take heat from the LED lamps to the other section. So this is how the cooling of LED lamps can be done. As we know, if you maintain the temperature of LED lamps, we can get a longer lifespan with the help of this particular we can say LEDs. Now next thing again the same, if you are cooling the LEDs or if you are cooling the electronic equipment, it means that you are ensuring the longer life of the electronic devices. Next thing, applications in electronic cooling. So that is quite a familiar example. You can see this kind of things in case of your laptops. The laptop uses pulsating heat pipe technology mostly to cool the we can say electronic equipment which are installed in the laptop. So the cooling of CPU is actually done with the help of the pulsating heat pipe technology. Simultaneously, you can observe a fan and some fins are also provided. So this is an example where we can use electronic cooling methods with the help of fan as well as with the help of a pulsating heat pipe technology. So next thing, the application which is in case of human body. As we know, underarms we have higher heat as compared to other part of the body. So in case of winter season, there can be some jackets that can be produced, so that will give heat to the portion where which is subjected to more cold condition, like say your hands. So the heat from the underarms can be given to the hand. So this kind of we can say the research is actually going on this particular we can say heat pipe which is used to wear in the clothes. So this is for thermal management or temperature regulation system of a human body. So again, this is one of the example where we are maintaining the temperature of LED lamp so as to ensure the longer lifespan of the LED. Another application is it can be used for graphics card. So thermal management of graphics card can also be done with the help of this pulsating heat pipe technology. Again, another example, a surgical probe incorporated in a cryogenic heat pipe is used to destroy tumors in the human body. The cryoprobe is a handheld device with a reservoir of liquid nitrogen and 12-inch heat pipe extension which is maintained at approximately 77 Kelvin nearly for 1/2 hour. So this is again one of the applications which relates to medical field.